hopefully by now you've kind of gotten into this habit of thinking about the behavior of the poles of a function, or of the impulse response of a transfer function, as being given by the location of these poles. And so if S is on the left-hand side of that plane, we know that it looks approximately like that. And as S moves to the right-hand side of the plane, we know e to the st starts looking like that. And we know that the sinusoids live on the real plane, and we know that on the imaginary line and on the real line, we know that there's no oscillation. These things just go up and down uniformly without any oscillation. Okay, so now we have to remember that the Laplace transform, or that the Z transform, is a Laplace transform. So we said, well, actually, if we take the Laplace transform of a sampled signal and we introduce this kind of fictive sampled signal idea that we get these deltas, the Z substitution is just an easy way for us to avoid writing a lot of E's, writing a lot of shifted E's. So we're basically saying, well, Z is e to the s times delta t. So we can see that there's a map that maps from S to Z, right? So this is now, that's now called Z1. But I want you to observe what happens to Z1. I'm just going to, so that is now the definition of Z, right? So Z is just equal to e to the s delta t. That was just our definition. I'm gonna enable tracing on this, and then I'm going to move S just along the imaginary.
D positive.
As it happens in this particular case, it doesn't really make a difference, but yes, let's just make D whatever. Okay, it really doesn't make a difference in this case, because the shape is what I want you to look at. So observe what happens as I move S along the imaginary line. So as I move S up and up and up, look at what happens to Z. Z eventually will describe a full unit circle. And this is a truth about the exponent on the complex numbers. You can explain this to yourself in a couple of different ways. You can think of this as being a graphical representation of Euler's rule. You can think of this being just the standard interpretation of completely, or the exponent of an imaginary number being equivalent to a rotation in the complex plane. Okay? Now, why is this important? Because you will have seen references in the textbook to stability criteria for discrete transfer functions. And you will have seen that in that diagram, and hopefully this is going to be really straightforward now, because in that diagram, you'll see that things outside of the unit circle in Z, and now, so how do I get outside of the unit circle in Z? Notice that as soon as I move from left to right, Z moves from inside to outside the unit circle. Is that making sense? And so when S is to the right of the plane, Z is outside the unit circle. When S is to the left of the plane, Z is on the inside of the unit circle. Every time, it doesn't matter where I am, if I'm on the left-hand side of the plane, I'm on the inside of that circle. As soon as I am on the complex line, effectively everything on the complex line just maps out being on that unit circle, and everything to the right just maps out being to the on the outside of the unit circle. Okay, and you can explain this to yourself through understanding of the exponential, and you'll see this is like a really repeating theme in this module. If you can invest like one thing that will give you super compound interest in this module is like understanding how E works, like in lecture 1. If you really understand how exponentials work, and if you understand how exponentials work on complex numbers and matrices and everything, then like all of the rest really gets a lot easier.